So I'm also sharing my screen. Okay, so yeah, we were looking at this notion of limit points of a set, and there was this question about whether you can have a set in which some of the elements are not limit points. Okay, turns out that the way I explained the limit points, there was one point that I missed. So we said that a point x is a limit point if there is a sequence in omega that converges to x. Okay, so one thing to note here is that the sequence should not contain the element x exactly. Okay, so it should be a sequence of elements other than x. Okay, so that's one thing. So like in the process of making things simple and giving you intuition, sometimes these things get missed. So there's another reason why you should definitely ask questions. So yesterday's question is what made me like go back and verify this thing. Okay, so this is the thing, right? There's a sequence not containing the point x that converges to x. So this is one way to look at limit points. The other ways it says is that x is a limit point if every neighborhood you take around the point x contains a point q which is not equal to x in omega. So let me just draw this. Yeah. Okay, so what this means is that you take a point x. Okay, so this is a limit point, and suppose this is the set omega. So any neighborhood you take, so suppose I'm taking this neighborhood. Remember, neighborhood is a region around x, such including all points, okay, within a distance of some epsilon. So that's an epsilon neighborhood. Okay, so this is written this way: a set of all y, such that y minus x is at most epsilon. Okay, so if you look at this neighborhood, then you should be able to find a point in omega. Okay, and that point should not be x, anything other than x. So any neighborhood you take, you should be able to find something in omega. Okay, so that is another alternate representation of limit points. So you could use either of these to check, and turns out that these two things are equivalent. Okay, so now to answer Siddharth's question about if there are points where the limit points are not in that set, I mean something where a subset of it is a limit point. So that example is just the set, right? The set of integers. So here there are no limit points for this set, okay? Because if you take 1, so this is the real line, right? So this is 1, 2, 3, and so on. So if you take this point 1, now if you construct a neighborhood around this, so this is, say, suppose within a radius of 0.5, here there is no other point other than 1 in this set. Okay, so this is not a limit point, and similarly all these points are not limit points. Okay, so yeah, so I hope this clarifies it. Okay, all right, so any questions on this? Is this notion clear to you all? So I think it was Siddharth Solanki asked, and there was a discussion with Siddharth Shah. You mentioned that you can have the constant sequence. So it turns out that that is not possible. That does not describe a limit point. Okay, is this clear? Any doubts? Okay, you're all quiet. What's up?
Yes, ma'am, it's clear for me.
It's clear. Okay, good. Okay, so this is the reason why you should definitely ask questions. Okay, like I can make mistakes, so you should interact, and so that things are clear. And please don't feel shy. There's no silly question or anything like that. Okay. Okay. So now today finally we'll move on to the optimization basics. So far we were looking at the preliminaries. So we looked at some things in linear algebra, calculus, and some things about the geometry of sets in terms of topology. So this will be needed to analyze optimization problems. So you all know that an optimization problem is of this form, right? So you have some function f of x which you want to minimize.
Ma'am, you aren't audible.
which will achieve the best function value. Okay, so just a
Ma'am,
second.
actually, you were not audible for say 20 to 30 seconds.
Oh, okay.
Yes, ma'am.
Let's see. Can you hear me now?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, okay. Thanks for pointing out. So, did you hear about the limit points, the clarification? That part was okay, right?
Yes, ma'am.
Okay. So, maybe I'll just start over here again from the optimization basics. So, you want, I mean, any optimization problem is represented in this way. So, minimize f of x such that x in omega, and the objective function is f. Okay, and omega is what is called the feasible set or the constraint set or the feasible region, and x is called a decision variable. Okay, so usually you will write an optimization problem as either minimize f of x or sometimes even maximize. Okay, so for this course we will go with minimization. I mean, we'll usually use the minimization representation, but you will see in a minute that you can transform forms between maximization and minimization. Okay, so by what do you mean by solving this problem? You're trying to look for a feasible point which achieves the best function value. So for a minimization problem, you're looking for a feasible point which gets the minimum objective value. Okay. So I just a second back I told you, like, if you have a maximization problem, you can equivalently write it in terms of a minimization. Let's see how we do that. So if you have max f of x in some omega, so it turns out you can write it in this alternate way. So you take the minimum of f of x, minimum of negative value of f of x, you minimize this form, and then you take the negative value. So just to see why it works, so this is a function, an example, okay, and this is on the region x in the x-axis. Now if you want to maximize this function, so this is the point, right, at which it's maximum. So x star is a point and this is f of x star. Okay, so now if you were to take the negative of this function value, so that's just this curve you see here. Okay, so this is negative of the function value, and yeah, it's like you reflect it about the x-axis. So that's just the negative value. Now here, if you look at minimizing this, you're going to get the same point, x star, but this value here, the function value, is minus f of x star. Okay, so by solving it, so by solving just the minimization problem without this minus sign, if you do, you're going to get negative value of f of x star. So that's why you take a negative of the optimal value of this minimization problem. So that's going to give you the same value as the max value. Okay, so just to see formally an example. So if you have this function max x plus 3y square subject to x between 0 and 10 and y between 0 and 5. So just by looking at this, you know that the values of the x should be as large as possible and the value of y's should be as large as possible, because this is increasing with x and y. So here the max value, so it's at these points, right? X is 10 and y is 5. And the objective is just this 10 plus 3 times 5 square. Okay, so that's just going to be 85. Now, if you want to write it as a minimization form, you just go ahead with minus x, minus of this function, the objective. So minus x minus 3y square. And the constraints remain the same. And then you take the negative of this. Okay, so it turns out that this will also give you the same value of v. Okay, so this will also give you 85. And the same values of x, the optimal x's and y's will be the same as this. Okay. Okay. So now, before we start analyzing any optimization problem, it's important to analyze the feasible region and the function itself. You should have some information about it. Okay. So one thing is, is the problem feasible? So is there any point in omega? So by this we mean, is omega non-empty? Okay. Next, you want to know is whether the function is bounded. Does the minima exist? Is it unique? So these are some of the questions you would like to answer. You'd like to get some sense of it. So let's just see some examples here in the real space. So this is all the region of X, and this is f of X. And I'm restricting my attention to this interval, okay? So this is a function I want to minimize. So here there is one minimum point, right? So this is the minimum, okay? So this is feasible because you have some elements in this omega, and the function is bounded in this range, right? In this omega, if you restrict it to omega, it is bounded in this region, and the minimum point exists, and in this case it's unique, okay? Now another example is here. So this is the feasible region, okay, and the function is this. So here, of course, there is at least one feasible point. Now in terms of it's also bounded in this region. Now here there are two optimum points. The optimum is not unique, so you're trying to minimize it, and there are two values here. So this is just to give you a feel that the minima need not be unique always. You can have multiple points at which the minimum is attained. Okay. Now another example is this function. So you're looking at this whole region is omega. This is the feasible region. Okay, so this is, yeah, of course, the feasible set is non-empty. Now the function is unbounded here, okay, because it keeps going, it keeps decreasing, okay, and you cannot find an end to it. Okay, so in that sense, so this is unbounded, and there is no minimum point here. Okay, so informally, that's the notion. Like you can keep on reducing the value. An example for this kind of an optimization problem is just this. We had seen this earlier, right? So you're trying to maximize x square plus y square subject to x greater than 0 and y greater than or equal to 0. Okay, so you can keep on increasing the values of x and y. So to write it mathematically, what would happen is you can find a sequence, okay, sequence of feasible points such that this value, the objective function value, goes to infinity. So the sequence here I'm talking of is something like this. Okay, so you start from x is 0, then you start with x is 1, y is 1, x is 2, y is 2, and so on. Okay, so it will diverge. It's not going to converge to any finite value. Okay, and all these are going to be feasible. Okay, now a final example, which we have seen examples similar in spirit. So there is a case where the function looks like this. So this is the starting point. So this is an unbounded region. In the set it's unbounded, but the objective function is e power minus x. So it starts from 0 at x is 0. I mean, it starts from 1 at x is 0. And this is the form, right, of the function. And this function is bounded. Okay, so it's always going to be greater than 0. Greater than or equal to 0, but there is no minimum point here. Okay, so the function is bounded, the set is unbounded. Okay, and you're not going to have a minimum, you're only going to have an infimum. Okay, so these are like different scenarios that arise. Now, this thing about minimum not existing, that can happen in different ways. So it could happen even when the set is bounded. It could happen when the function is unbounded. I mean, there are different scenarios it can happen in. Okay, so just it's always good to get a sense of what you're trying to solve, before you actually solve it. Okay, so again, when you solve an optimization problem, you either want to obtain an optimum, or you want to identify that an optimum solution doesn't exist. So either it's unbounded, or only infimum is there, there's no minimum, something of that sort. So these are the things you want to identify. Okay, so any questions so far? Am I audible now? It's all good?
Yes, ma'am. Yes, ma'am.
Okay, so far all good, right? Like you're able to understand?
Yes, ma'am. Yes, ma'am.
Okay, good. So so generally we say an optimization problem is unbounded if you have a a sequence of feasible points which converge to minus infinity in the case of minimization, and for maximization you have the sequence which goes to plus infinity. Okay, so this is how you explicitly say that the problem is unbounded. So now we're going to start with unconstrained optimization, which is a case of an optimization problem where the feasible set is all of Rn, okay, or the set of all real numbers that forms the feasible set. So it's minimize f of x in Rn. So where does this kind of problem occur? Does it come up in any places? Like, is it only constrained, or you have unconstrained optimization instances, or how is it? So for doing that, I've just constructed some examples here. So one is, again, the IIT Goa campus design, right? So earlier we saw a use case where you wanted to position some security guards. Okay, so now we're looking at a different problem here, where you want to position the hostel block. Okay, so some things are already done, like you have a mess, you have some of the departments and the labs, and there's also a shop, and you want to, in the midst of all this, you want to position a hostel block appropriately. Okay, so now you want to position it in such a way that you're close to all these areas which you will tend to visit often. Okay, so this can be written as an optimization problem like this. So where each of these, the position of the mess, you can denote it as yi. So it's a coordinate in 2 dimensions. And so this is y1, and the departments you have something like y2 to say yd, and like that. Okay, so you have each of them which is specified by the coordinates y. Okay, so this is in R2. So yi's are in R2. And you want to find x. So x is also in R2. Okay, you want to find the location, the best location, such that it's close to all of them. So this is the norm. So the 2 norm, if you remember, which we saw earlier. And yeah, you're just trying to minimize the square of the 2 norm between the two. Okay, so this is an unconstrained problem. So there are different variants of this, and this is actually referred to as the Fermat-Weber problem. Okay, now there are different notions you can have here. Suppose you have something like weights. Okay, so so each of this is multiplied by weight. Okay, so some things are more important to you, maybe. Maybe it's not very important to be near a shop because you probably don't go every day, but maybe it's more important to be near a mess. Okay, so some things of that sort can be captured by having these weights. Okay, now here the problem that you want to do is minimize, right? But if there are some things you want to maximize, that you want to be far away from some parts of this, some locations, then you will get another problem, right? You'll get some maximization in some sense. So yeah, these are different variants of the problem, but some variants are easy and some are hard. Okay, so even unconstrained optimization problems can be hard. Okay, so remember the notions of hardness that we introduced in the first 2 lectures. So yeah, so that applies even to unconstrained problems. Not every unconstrained problem is easy to solve. So another example I want to give you is in machine learning. So many of you doing the machine learning course, so at some point you will come across this, but just to give you a sense of where optimization of these kinds, problems of these kinds appear. So this example is called linear regression. So to understand this, suppose you own a real estate business and you want to know the value of some house. You have a client and you want to predict what's going to be the value of that house. Okay, and to do this, you have some data to help you. And there are some features. Okay, so each house is described by its size, the floor, number of floors, or if it's an apartment, like which floor it lies in, then the locality, and those kind of things. Okay, and so these are the features. These are called the features, and that is available to you of this particular house. And additionally, you have some data corresponding to these features of some other houses. Okay, and also the prices of those houses. Okay, so this is called the training set. So these are the data points in some sense. So there are n such houses with the details of which you already know. So x1 is a vector which says the features. So this is suppose there are m features. Okay, so this is going to be a vector of size m, and this is going to be a single number y. Okay, so you have n such tuples. Now, one assumption that you could make is that the price is a linear function of these features. Okay, so you don't know this. How how each of these features affect the price, but you assume that it's a linear function of this, and now you want to find this beta vector. Okay, so remember x is a vector of size m, so there are m features, y is a single number, and beta is the importance you give for each of these features, and that is also a vector of dimension m. Okay, so ideally, if you have this assumption, you want all these y1 to yn to have this linear form, right? So y1 is beta transpose x1, y2 is beta transpose x2, and so on. Okay, and then one way to do this is, you solve this system of equations. Okay, whatever I wrote here, it's just exactly this. Okay, so this is if everything was nice and you knew all the prices and the prices were this model was perfect. But many times what happens, and almost always that's the case, that this y1, I mean, all these y's are not exactly going to be representable as beta transpose x. In the sense, you will have some noise term, okay, some epsilon1, some epsilon2, and so on. Okay, so these are some noise terms that get added. Okay, and so that's why you are not going to have a perfect solution here. Okay, so you will remember, like a system of linear equations, you may or may not have a solution always. So for these kind of problems, you will mostly have this noise term which is there. So if you just try to solve this x transpose beta equals y, you're not going to find, most likely the solution is not going to exist. Okay, so then that's the reason why, okay, so now you relax your notion, you don't want to find the betas exactly. So what you do is you instead try to find the betas such that this difference is as low as possible. Okay, so this y minus beta transpose xi, that's like, it's there's some sense of loss that you have. Okay, and this is as low as possible. So you want to find the betas. Okay, so the optimization variable here is the betas. Okay, so this is called a least squares problem actually. Okay, this comes up in linear algebra also. I'm sure you probably might have seen it there too. Okay, so any questions so far? Any questions? All good? Okay. Devan says no questions. It's clear. Devyani says it's clear. All good. Okay. 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 Cool. So it's all good. Fine. So these are some motivating problems that we have. So now, before we go to even think of solving it, let's get this ideas of local and global optima. Okay, so what are we actually looking for when we try to solve a problem? So suppose there is a minimum point. Even further, if you try to solve it to greater granularity, what is it that we are looking for? So to do that, you need to see that, like, that's the notion of this local and global optima. So if you have a function like this, right, that you want to optimize, it's an unconstrained problem. Now, there are different points here, okay, which are actually of interest many a time. So the best point here, which minimizes this function, so this is f of x. And if you want to find the absolute best point, okay, so that would be this, right? This is this point here, okay? So this is called the global minimum, okay? That it is better than every other point in the feasible set, okay? Now, what about these points here? Okay, so there are some other points here which are they're okay. I mean, they're not as good as the global minimum, but you can perhaps live with these. So because they're better than some other points in a region around it. Okay, so this is also maybe something which is desirable. So these points are called local minima. So you have two here, then you have one here. Okay, so in this region, if you see around this, in this locality, this is the best. Okay, and similarly here too. Okay, so these are local minima. Now, similar analogous notions exist for maxima as well. So these are like local maxima. Okay, and yeah, and so one thing you should remember is even these global minima, they are also local minima. Okay, because even in the region, in a local region, they are good, but of course they are even stronger. They are globally the best. Okay, and there's also this notion of saddle points. Okay, so something of this form here. So here you see that the function, it's not better than everything in this area. In some, it's better than some in around it, but it's worse off than some others in the locality. Okay, so it's increasing in one, the function increases along one direction, but decreases along the other. So those kind of points are called saddle points. Okay, so these are some notions that are useful. So to characterize them mathematically, so x star is a local minimum if you can find a neighborhood around it such that f of x star is less than or equal to f of x for all x in that neighborhood. So this delta is what helps you identify a neighborhood. Okay, so that's exactly the notion, right? A local region around it, you are better at x star. Now, in the case of global optimum, the global minimum, x star is a global minimum if f of x star is less than or equal to f of x for every x. Okay, so that's why this is the global minimum. Okay. All right. So, what do we want? Do we want a local minima or do we want a global minima? What are your thoughts? What do you think we are looking for? Like global, right? Global, right? So always we would like to have global optimum, but turns out that many times finding the global minimum is not always easy. Okay, and many times even finding the local optimum points is also not easy. Okay, so but for many problems you can somehow get the local optima, but global optimum it's very difficult to find. So yeah, so that's the reason why for several problems people are just happy with local minimum. So that's the case even in life too, right? Like you don't know where things are heading. All you have is the current point. Some points around you to make decisions. You have the current situation and you probably have some sense of what is going on around you now. But you never can see like far ahead into the future about what would have been best at this point. Okay, so that's the issue, right? You don't have a lot of information to make this choice to find this global optimum. And sometimes it could also happen that you spend so much of energy in trying to find the global optimum, but one thing is so much efforts are spent, and also maybe the global optimum is not so much better than the local. Of course it's better, but maybe the difference you could live with this local itself. Okay, so the difference maybe it's not too large, who knows. Okay, so that's the reason why for a lot of problems people spend their efforts finding local minima rather than global optima. Okay, so that's going to be the focus of this course too. Okay, all right. So, any questions till now? All okay? You're all very quiet today. It's all clear. Okay. All okay. Fine. Okay. Good. So now let's go into, so having set the base for optimization problems, let's go into, some characterization of these local optima. So some of these things, some variant of it, you probably would have learned it in your school days or even after coming here, but you need some rigorous notion to see like why these conditions hold, and that's what we will do today. So first we'll come to this thing called first order necessary conditions. So what it says is that if you have a differentiable function and suppose x star is the local minimum, suppose somebody told you that x star is a local minimum, then it must be that the gradient of f evaluated at x star, that is 0. Okay, so so this probably you guys are familiar with. So it's a necessary condition, but it's not sufficient. So any thoughts? What does this mean? What do you mean by this is a necessary condition but not sufficient? Anybody?
Ma'am, if the condition is satisfied, it need not be that it's not guaranteed that you'll find it, but in order to find it, it has to be there.
That's the first level of check.
First level of check, right? So all these points are valid. So if you have if you know that x star is a local minimum, then this is 0. But suppose you somebody gave you a point for which gradient of f of x star is 0, it doesn't mean that x star is a local optimum. But at the same time, if you have a point x such that gradient of f of x star, gradient of f of x. So suppose you got this as something like say 5. Okay, so then definitely you can rule out that this is not an optimum. Okay, so that's what it means by a necessary condition, but it's not sufficient. Okay. So now, since it's not a sufficient condition, we have this notion of critical points. So any critical point is a point such that its gradient is 0. So one possible way to find the local minimum is to find all the critical points, and these will serve as candidates, right? So you see all the points, you try to find the points for which the gradient is 0, and then you have to do something more. Okay, but it helps you eliminate a lot of points which wouldn't be local minimum. Okay. So let's take an example here. So in this case, so f of x is x1 square plus 0.5 x2 square plus 3 x2. So can you tell me the gradient? So what's the gradient? Guys, what's happening?
2x1 and x2 plus 3.
2x1 and x2 plus 3, right? Okay, so so now the critical point here is just, so this has to be 0, and so you just take x1 is 0 and x2 is minus 3. Okay, so so these are the critical points. Now you have to see whether this is actually a minimum or not. So for that, these contours are going to help you. So let's just see that. So so I'm just taking all the points in the range minus 10 to 10. Okay, and this was the point, right? X square plus 0.5 y square plus 3y. Okay, so now I can actually draw the surface plot for this. Okay, so the surface plot is actually going to, give you an idea of the shape of the function. So this looks like, it has some minimum point somewhere here. Okay, so so now if you draw the contours, you will get a better idea about the function. So you can see here, right? So these are the contours, and perhaps this point 0, the point we had was 0 and minus 3. So 0 and minus 3 somewhere here, right? So perhaps that is indeed a minimum point. Okay, so yeah, that's how you, but this is just to find the critical points. So now if you see, let's take this other function with just a small difference. Okay, so it's just instead of plus 0.5, there's a minus 0.5. So here the gradient is what? 2x1, the same thing, right? Minus x2 plus 3. Okay, so if you had to set this to 0, what would you get?
Ma'am,
What would
X0.
you
0,
get here?
3.
Yeah.
Yeah, so x1 is 0 and x2 is 3. So let's just see what this would look like here. Okay, so that would be this function. Okay. Okay, so here you see that there is some kind of, at this region, there's some kind of, it's not a very regular surface, right? I'm using the word regular very loosely, but it's not that, like the function is, seeing this, you can't tell whether, it's a point of minimum or maximum or anything. Okay, in fact, this looks like a saddle point, right? A point where, along one direction it reduces and in another direction it increases. Okay, so it turns out that that's exactly what happens here. So for the point 0.3, the objective value here, if you evaluate, this is going to be what? x1 square is 0. So here it's going to give minus half times 9 plus 9, right? So this is going to be 4.5. Okay, so if you can actually see that what it looks like, that point where it fits in. So let's just do that. So, okay, so it's somewhere here. So this red point that you hear, that is the point. So here you can see, like, from this plot, it looks like it's increasing along this direction, but perhaps it's decreasing along this direction. Okay, the function value. So it's not clear. So this doesn't really look like the minimum point. And in fact, it is not the minimum. So you can also verify this by looking at the contours. So I've also explicitly drawn this minus 4.5 contour. So this function, it doesn't look like, a very, so this, you can see points where things are becoming like a crisscross kind of a thing. So that is indicative of what we call as saddle points. Okay, so, so these are examples of where, if you have this gradient is 0, it doesn't necessarily mean that you have reached an optimum. Another example which is popularly used is the case where f of x is x cubed, just the single dimension one, a single dimension function. So here if you take gradient f of x, so it's just f dash x, so that is 3x squared, and this is 0 at x equals 0. So you should try to see what x cube looks like. I mean, I guess you guys are familiar with it. So it would be something like a saddle. So it looks like something like this. Though at this point, this is not a minimum point. Okay. So just to get an idea of why this is true, the proof of these conditions. So the idea is that you're given that x star is a local minima. So there is a neighborhood around this where f of x is, every point in that neighborhood is greater than or equal to f of x star. Okay. So there is some radius you can find, there is some r there. So then the idea is to, you just take some direction. So you take all possible directions here. Now you try to evaluate the gradient of this function, f of x star plus alpha y. Okay, so I'm going to define a new function, g of alpha. Okay, so this depends on alpha. So I'm fixing the direction y. Okay, so let me just write it. So there's an x star and there's going to be a direction y. Okay, so I can move different steps along this direction. Okay, so I can move along alpha. Alpha can be very small, so then I'll just stop here. Or alpha can be large, in which case this will be my x star plus alpha y and so on. Okay, so now if I take the gradient, so the derivative with respect to alpha, so you do that by doing chain rule, right? So you take the gradient of f and you evaluate it at the point x star plus alpha y, and transpose this inner thing, whatever function you have inside this, which is a function of alpha. So you have this transpose y. Okay, so it's just an application of chain rule. Okay, now just to understand this further, so g of 0. So g of 0, so this is alpha is any step you take along this line. Okay, alpha is a step in this direction. So if you set alpha equals 0, what are you going to get? So what is g of 0? G of alpha is 0. So what is g of 0?
I'm f of
Anybody?
x star.
F of x star, right? Yeah, so just substituting alpha is 0 here. So that's going to give you f of x star. Okay, so now let's just take what happens around this. So the idea is you're taking what happens in a small region around x star. Okay, so by the definition of derivative, right, you know that it has to be this thing, right? Around the point 0, when you take alpha as 0, what you're going to get as its derivative is just the limit of this quantity. Okay, the rate of change of this g for a small difference for a small step along the direction, right? For a small change in beta. Okay, so so remember that limits, right? So you can, I mean, when we say that this is limit for the case of derivative, it has to be that whether you approach it from the left or from the right. Okay, from whether you approach 0 from the left or from the right, you're going to get the same thing. Okay, so let's just take the when you approach it from the positive values. So beta, maybe you start from 0.5, then you go 0.4, 0.3, like that, and you find it at 0. So then this is the expression you have. And so if I'm just expanding this, so g of beta is just going to be f of x star plus beta y. So just applying this, okay? Okay, and g of 0 is just f of x star. Now you know that for a small region around x star, this quantity is greater than 0. Okay, why? Because x star is a local minimum. So around the vicinity, this quantity is greater than 0. So, and you're looking at only the positive values of beta, and so this whole thing has to be greater than 0. Okay, so now recall what g prime of 0. So this is to show that this is greater than 0. The derivative takes a value greater than 0. Now another expression, from this expression, when you apply chain rule, we have this, right? It's delta f x star transpose y. So that is, so this is g prime of 0. And this you get from chain rule by substituting the value of alpha in chain rule. Okay, and so this has to be greater than 0 from here. So these two are actually the same, right? These are the same expressions. I mean, same, they're quantifying the same value. And so these have to be greater than 0. And this is true for any y you take, okay, because x star is a local minima. So now if you take minus y as another direction of the move, instead of moving along y, suppose you took another direction y, so minus y, okay? So this is a straight line, pardon my drawing. Okay, so if you take minus y, then applying the same steps, what you're going to get is minus delta fx star transpose y is greater than 0. Okay, greater than or equal to 0. So the only way both these can happen simultaneously is when delta fx star transpose y is 0. Okay, and this has to be true for every y. And so now if you take y as each of the coordinate axes, right? So if you take y as 1, 0, 0, 0, what you're going to get is the first component of the gradient is 0. Now if you take y as this, you're going to get the second component of the gradient as 0, and so on. Okay, so that's why you get each component of gradient fx has to be 0, fx star. Okay, so that's the proof for the first order conditions. Does it make sense? All okay? Please ask if something is unclear. It's clear? Okay. Once it's clear, Siddharth, it's clear. Shivam, it's clear. Kishan, yeah. Okay, good. Okay, okay, good. So have you seen this proof before? Somebody want to answer? Have you come across a proof of this before? Come on, guys, that's an easy question, right? It's yes or no.
I cannot recall exactly, but I think we have seen this in multivariate part of the calculus course.
Calculus proofs, right? So yeah, so this should be kind of straightforward. So I think you guys all would be quite familiar with using it, right, to find the critical points. But now this is the reasoning for why it works. Okay, so so now like you can also have some further conditions. So I think I'm running out of time, but I would like to also finish the second order necessary condition. So if you have some other class or something after this, you can go on, and we'll be posting this online. Okay, so I'll probably take about 10 minutes more. Okay. Okay. So yeah, feel free to leave in case you have some other work. Okay. So in the first order conditions, we only look at the first derivative, right? The only thing we said was the gradient is 0. So now, suppose you have many points in which the gradient is 0. Is there something more you can say to eliminate? Can you eliminate more points? Okay, so for that reason, we have the second order necessary conditions. So what it says is that if you have a function that's twice differentiable, and x star is a local minimum, then in addition to the gradient being 0, the Hessian, the second order derivative at the point x star has to be positive semi-definite. Okay. So again, in the same way, this is a necessary condition. So if you have some point where this is not true, the Hessian is not positive semi-definite, then immediately you can discard it, saying that that's not the local minimum. Okay. Right. So let's see how we do this. So this would make use of the Taylor series expansion. So recall what we have is this f of x star is less than or equal to f of x for all x in the neighborhood. And you also just proved that the gradient is 0, okay, at this point. So now the Taylor series expansion, that's what we're going to use around the point x star. Okay, so the same idea. So around x star, if you see, some other point you take, you approximate it with the second order expansion, and it should be such that the function value at this point is going to be greater than x star. So that's the idea, that's what we will use. So recall that the second order expansion was this, right? F of x star plus you had this term alpha y transpose delta f x star, and a term which depends on the Hessian. So it's exactly alpha square by 2 y transpose delta f x star y. Okay. So this is just, I'm just plugging in the approximation, the Taylor series approximation. And there is this term, which is small o of alpha square, which is a very small term. Okay. So, so now when I just bring these together, so this term is going to be greater than or equal to 0, that we already know. And this is true in a small neighborhood. So you have this R, which dictates to you how much you can go. So what is the limit to which you can go? That will depend on this R. Okay, so but anyway, for small values of alpha, this is going to be greater than or equal to 0. Okay, and now we have this right hand side. Okay, so because this is greater than or equal to 0, this whole part is also going to be greater than or equal to 0. So just to recall, what does this mean? Okay, so this is a quadratic term. Okay, and we have this term, which is O of alpha square by alpha square. So what this means is that in the numerator, we have a function, some g of alpha. Okay, so that function is small o of alpha square. Okay, that's what this means. So there's a function here which satisfies this, that the limit as alpha goes to 0, g of alpha by alpha square is 0. So this is just by the definition of O, okay, the small o. Okay. Okay. So yeah, that's what this means. So remember, like what we mean by this, the limit alpha goes to 0, this quantity is 0. It means that for every epsilon you take, you can find a region delta such that whenever alpha is within delta, you have this function value g of alpha by alpha square is less than epsilon. Okay, so for any epsilon you have, you can compute. You can have this delta. It's possible to find a delta, and this relation is true. Okay, so what this means is that you plug this back here. Okay, so this g of alpha by alpha square is exactly this O of alpha square by alpha square, and that is less than or equal to epsilon. So bringing it to the other side, you will get that this quantity, this quadratic term, is greater than or equal to minus epsilon. And the main thing is this is true for every epsilon. Okay, so this is true for every epsilon. For every epsilon greater than 0, it's true. So if you have epsilon is epsilon is 0.5, so this quantity is going to be greater than minus 0.5. If you have epsilon is 0.1, you can find some delta here. So overall, this quantity is going to be greater than minus 0.1. So you can keep on finding smaller and smaller values of alpha. So because of that, smaller and smaller values of epsilon. Okay. So because of that, we can say that y transpose this term, this quadratic term, is going to be greater than or equal to 0. Okay, because any epsilon you take, you will have this relationship. Okay, and now remember, y was just any direction. Okay, so any direction around x star you could go. Okay, so that's why this is true for all y. Okay, so this is nothing but this is what is a positive semi-definite matrix. So this means that the Hessian, this delta square f of x star, is a positive semi-definite matrix. Okay. So any questions on the proof? Is it clear? It's clear? Okay. What about the others? Are there any questions? It's clear? Okay. Clear. Hashir says it's clear. Clear. Okay. All right. So, I guess it's clear to you guys. Okay. So another thing, yeah. So whatever we had so far was the necessary conditions. Okay. Now, when do you know that you're done? Okay. So how can you confirm that if I have this condition, I know that I've reached an optimum? And for that is what we have, these sufficient conditions. Okay. So I'll just state the condition and then maybe I'll do the proof in the next class. Okay. So if a function is twice differentiable as before, and suppose you have a point such that the gradient is 0, and the Hessian is positive definite. Okay, so not positive semi-definite, but this is positive definite. Okay, so what do you mean by that? All its eigenvalues are greater than 0, right? Strictly greater than 0. So for such, if you have the Hessian satisfying this property, then you can say that x star is a local minimum. Okay. So it's just a small difference that this has to be positive definite for the sufficient condition, but whereas it is necessary that it's positive semi-definite. Okay. So now this is not the only condition. Okay. So it doesn't mean that, so this is not a necessary condition in the sense that you can have a local minimum which doesn't satisfy this property also. Okay. But if it does, if there's a point which satisfies these properties, then surely it's a local minimum. That's what is meant by sufficient conditions. So in the next class, I will give a proof of this. And also we will look at some ways how you can apply this on some examples. Okay, so That's the plan. So you would need some linear algebra background for this part as well. Okay, it's mainly about spectral decomposition and these eigenvalue decompositions. So yeah, just a heads up. Okay. So any questions? You're all very quiet today. What's happening? Is it like weekend effect, afternoon effect? Are things okay?
Ma'am,
Yes.
could you please again repeat how did we prove the previous statement? Like on the last line when like y transpose Hessian of fx star y greater than or equal to 0. So after that, how did we say that the Hessian of fx star is PST? Means actually the thing is I didn't understand what we in the PST.
Oh, okay. So this is positive semi-definite. Okay. So this matrix, so this is a matrix, right? The second derivative. Okay. So is it clear how we came till this point? Up to
Yes,
this
ma'am.
point is
Yes.
clear. This is clear, right? So what? Okay. So let me just recall positive semi-definite matrix. So matrix is positive semi-definite if you have that. So if you want to say matrix A is positive semi-definite, one condition is that for every x, so this A is fit as R n cross n. Okay. So then every x in Rn, you're going to have x transpose Ax is greater than or equal to 0. Okay. So this is a characterization of positive semi-definite matrices. Okay. So there are many characterizations. So one is all the eigenvalues are greater than or equal to 0. Then the other is this thing, right? For every x in Rn, you're going to have that this quadratic form is always going to give a value which is greater than or equal to 0. Now there are some other things. You can have a decomposition of this form. A equals some decomposition like this in terms of a lower triangular matrix. So there are several such equivalent representations or characterizations for positive semi-definite matrix. So the one we have here is this one. Okay, we are going to use this particular one. Okay, so this is clear, right? So y transpose delta square fx star, this quadratic form is going to take a value greater than minus epsilon, and this is true for every epsilon. So you can say that this is the only way this can happen is if it is greater than or equal to 0. Okay, right? So this part is clear. How you go from
Yes.
this step to
Yes, ma'am.
clear. So after this, it's just you're just making use of the characterization of semi-definite matrices, and this is also true for every y. So is that part clear? Why it's true for every y?
Yes, ma'am. Because we took y to be any direction.
Yes. So exactly. So any direction you can take around x star, and you will have you will come to this point. Okay. So that's why. So this is just another way of saying that the Hessian is positive semi-definite. Okay.
So, ma'am, we are yet to prove that the Hessian of fx star is greater than or equal to 0.
So what we have shown right now is the Hessian is so greater than or equal to 0. It just means, so this is just meaning that it's positive semi-definite. So this doesn't mean that it's entry wise greater than 0. That's not the meaning. Okay, so I think I see where the confusion's coming. So if you have a single, so if this function, so suppose you have this function is from R to R, okay? So it's just f of x, something like say x square, okay, 3x square, something like that. So then, yes, if you take the first derivative will be what? F dash of x is going to be a single number, okay? So this is going to also be an element of R. So this is going to be an element of R. Now the second derivative, so this Hessian here is just going to be the second derivative here, right? So it's also written in this manner. So this is also going to be R. Okay. So now, yeah. So for this case, what you will get is this equivalent condition is f double dash is greater than or equal to R. Okay. So because think of a matrix having just a single entry. So it's just one single number in a matrix. and that is positive semi-definite. So that's what this condition is. So that for this case, it's just that this entry has to be greater than or equal to 0. Okay, was that the question?
Ma'am, actually my question was that did we prove that that the Hessian of fx star is greater than or equal to 0, so that we can say that this condition is sufficient?
No. So what do you mean by greater than or equal to 0? So here,
Actually, ma'am, we said that for this x star to be a local minimum, we have to say that the Hessian of fx star should be greater than or equal to 0, because we had already proved that the gradient of fx star is equal to 0.
yes.
So after that, to prove the second order necessary condition, you have to say that the Hessian of fx star is greater than or equal to 0.
So by greater than or equal to 0, what we mean is it is positive semi-definite.
Okay, ma'am.
Okay, it's yeah. So greater than or equal to 0 doesn't mean that. So Hessian is a matrix, right? So greater than or equal to 0 doesn't mean that the elements of that matrix are greater than or equal to 0. That's not the meaning. So the meaning is that this matrix is positive semi-definite, right? So that's what we have shown now in this proof.
Okay, ma'am.
It's clear? Okay. Okay. So yeah, any other questions? Anything else? Any concerns? You guys have to speak up. You have to tell me what's going on. Okay, I think I should ask people. What about Viransh? Is it clear?
Yes, ma'am. So far.
So far clear? Okay. What about Devyani?
Yes, ma'am. I'll just have to do the proofs on my own ones. So,
Okay, sure. Sure. Yeah, so the proofs, yeah, you can take some time, go over them slowly, and we can again come back to it if there are questions. So anything else? What about Rajneesh?
Clear, ma'am.
It's clear? Okay.
And I mean, exams, this sort of proofs will be not there, yeah, right?
So you have to understand these proofs because these proofs are critical, right? I mean, you should know why these conditions are necessary or why they are sufficient. Okay, so
I mean,
just understand the logical sequence of steps. Of course, I won't ask you to prove this whole theorem as such. So that's not something I'll ask you. But yeah, you should understand why it's true. Otherwise, it will just be some facts, and you don't know why you're doing this, right? So okay. Anybody else? And how are things going? Jaswant Gurti.
Yes, ma'am.
Are you there? It's clear?
Yes, ma'am. It's clear.
It's clear. Okay. Harsimran, how is it? It's okay?
Yes, ma'am.
Okay. Okay. So, yeah. So, anyway, we will see how to use these concepts in the next class. So, maybe, yeah, you will just get a little more comfortable and at least using it, right? So, that is also an important thing. Okay. So, yeah, if there are no more questions, I think, yeah, we'll call it a day. Okay. So, thanks, everyone. Have a good weekend.
Ma'am, the Tuesday class will be on 8:30 or 9:15.
So it will be at 8:30. So some of you have indicated that you have some other work at that later on. So that's the reason. So we'll stick to 8:30 itself.
Okay, ma'am.